the normal stress. Okay, so the normal stress, right? So the normal stress, what we can do is the normal stress, right? So now just use Mohr circle now. Okay, so the normal stress of y beta. I think I can switch this to this mode now. Now the normal stress for y beta is equal to stress average, right? Minus minus the what? Minus the radius or tau max, right? Tau max. Hold on. I'm having a brain fart. Oh wait, let me do some side work. Tangent to beta. Oh no, I'm going to use sine cosine. Cos to beta, right? Why I have selected that is because this distance over here, right? Right, this distance is tau max, because over here, this value over here, I'm going to draw in green, right? This is our radius, and our radius corresponds to our tau max. Okay, so tau max to beta, and from here we know that stress average. Note that stress average is equal to P over 2A, right? And it happened to also comply to tau max is equal to P over 2A. Okay. So if I were to rewrite equation 1, stress y beta small y, do apologize, stress y beta is equal to P over 2A, then minus P over 2A, right? Cosine 44, or 2 multiply, so beta, let me confirm, is 2244. Okay, so we have everything now. Okay, so we can find what is our P, right? So stress y beta, we were given that this is 400. Let me check. 400 times 10 to the power 3. So this is equal to P over 2. The cross-sectional area is what? Let me see what's it. It's equal to 0.08 multiplied by 0.12. Okay, so 0.08 multiplied by 0.12, right? And then I'm going to do 1 minus by cos 44. Okay, make sure it's in degrees. Cos 44 is equal to 0.719. Okay, so 40 times 10 to the power 3. Let me check. P2A 1 minus, okay, this guy. So P is equal to 400 times 10 to the power 3 multiplied by 2, 0.08, 0.12, and then divide by 1 minus by 0.719. So let me do cos 44 first. Yes, so 400, I'll change my bracket. So 400 power 3 times 2 times by 0.08 times by 0.12 divided by 1 minus by 0.719. close bracket. So it's equal to 27.333 or 27.331 times 10 to the power 3 Newton. Okay, so that is our P value. Okay, so let's check. Yeah, so over here we get 27.4. I got 27.333. Okay, so we are not that far. Okay, we're pretty close, right? So that is one value based on what? This is based on normal stress. Okay. Now there's another value that we can get, okay, and that is based on shear, because based on shear is going to be 600. Okay, so to get a shear is pretty straightforward, right? So I'm going to yeah, I'm going to do on the let me see. Is there any way I could squeeze? No, I'm going to do on the new page. Okay. Let's get the diagram over. Right. So now we are going to form the equation based on shear, right? So we are going to form shear y beta. So this will be equal to the radius, which is or this is equal to tau max sine 2 beta, right? So we know that tau max, note that tau max is also equal to P over 2A, right? It's obvious down here, right? Because one point is 0, the other one is x, right? So P over A, so the average is P over 2A, the center of the circle. So from here, we will have 600 times 10 to the power 3, and this is equal to P divided by the cross-section area to 0.08, 0.12, right? And then we have sine 44. Okay, so therefore P will be equal to 600 times 10 to the power 3. 600 times 10 to the power 3 multiplied by 2, 0.08, 0.12, and then the whole thing we divide by sine 44, right? So this will be equal to 600 times 2 times 0.08 times 0.12 divided by sine 44 is equal to 16.58. 16.584 times 10 to the power 3 Newton. Okay. And this is due to the what? To the shear stress. Okay. So we have to pick the lower one, because if P is larger than 16.584, the joint, okay, the glue will fail due to shear. Okay, so therefore, right, the previous one that we got, right, so this is due to normal stress, and the other one is due to shear. So therefore, the P allowable is equal to 16.584 times 10 to the power 3 Newton. Okay. So if you look at this, it's so much more straightforward solving this by using Mohr circle. The most important thing is you have to be capable of identifying where this point is. Okay, so if you look at the solution manual, it does the same thing. Okay, very similar stuff that we have done. Okay, and you look at the equations are very similar, right? Very similar, or not similar, they are the same equation. Okay, now the next question that I'm going to do before I go on any one have any questions? I'm looking at the chat. We are okay so far. Okay, I'm going to do a very similar question again. Okay, and I want you all to like be able to visualize what is going on is more important than anything. No memorizing. Okay, as you all have been through term test 1, to do this deal with this class, you have to analyze. Okay, the analysis is more important than memorizing or formula whatsoever. Okay, it's the analysis. Right. So let's deal with another problem. Very similar similar sort of format. Okay. So this is example number 2. And you will see what changes. Okay. Right. Now it's important that you understand the questions individually and not I realize a lot of students, okay, I'm not saying it's you, but when I'm teaching this for the 18th time, a lot of students compare the trend of one question to see whether would that help them. No, okay, because every question is unique, every question is different. Understanding the concept is more important than anything else. Okay, right. So 2 members of uniform cross section, 50 and 80 millimeters, are glued together along plane AA. Okay. That forms an angle of 25 degrees with the horizontal. Okay, as you can see. Knowing that the Blauvert stress for the glues are at normal stress 800, the shears at 600, determine the largest P value. So you can see where the similarities. Okay, but you have to apply the concept that we have learned. That's more important. So the first thing we do is we are going to call this X, okay, and we're going to call this Y. Okay, so now we are going to draw an element. So this is X, and this is Y, and this is our first element that I'm sketching now. Right. So over here, now we have a load coming down over here. This is equal to P over A, not P over 2A. Okay, force divided by area. Right? And if that's the case, an element, if it's tensile on the top, it's also tensile. So we're going to label this point X. We're going to label this point Y. And from here, we now realize that stress X is equal to 0, right? Stress Y is going to positive P over A, and shear XY is equal to shear YX, and this is equal to 0. When this is equal to 0, this is the principal plane orientation because 0 shearing stress. Okay. Now, so that's all we have. The next thing that we have now, right, is we are going to rotate it. So you can see me putting the triangle there, rotate to what? 25 degrees, like what it is saying. Okay. So we rotate this way now. Okay. So now when it rotates, again, we will label this our point Y, right? Then over here, this will be our Y beta. And over here, this will be our X beta. And we know that the Y beta, the normal stress, okay, as I said, very similar. The normal stress is moving at 800. Times 10 to the power 3 Pascal. The shear we don't know which direction yet. Okay, so the shear x or shear y beta x beta